Hi, my name is Jessie. I'm a human-computer interaction master student at the University of Würzburg, and I worked on the virtual audience animation project for the University of Würzburg's virtual audience simulation system. First of all, what are virtual audiences? Virtual audiences are meant to simulate the feeling of standing in front of a real-life audience while giving a speech or doing an interview. They can be used for speech training and social anxiety therapy. The audience is made up of virtual agents that show different behaviors to create the illusion of a real audience. To do so, animations are needed. However, animations are time-consuming and difficult to make. Professional animators receive years of intense and expensive training. There is a method to make animation easier called motion capturing. It works by recording the movements of a real person and mapping these movements to a 3D character's skeleton. This process requires multiple cameras to record the same scene at the same time and a special suit worn by the actor. This suit is skin-tight and completely black. It is made out of a Velcro-like material, which allows for small reflective spheres to be attached to it. The recorded video is then interpreted by specialized software which is looking for these reflective spheres. The benefit of motion capturing is that the resulting animations will look very natural, as they are directly based on real movements from a real person, and are less time-consuming in production. I used this process for creating some of the animations for this project. I will describe the entire animation process and outline a sort of pipeline one has to go through to create animations using motion capturing. For a more tutorial-style write-up of how to do this, please have a look at the Git repository for this project. The motion capturing system used uses OptiTrack hardware and their Motive software. Once the setup is completed and the actor is wearing their suit, the recording process is rather straightforward. However, motion capturing is prone to errors. Sometimes the software might not recognize the spheres, or they might be hidden because of overlapping body parts. Motive provides some features to correct these errors afterwards, but this must be done manually. It is also worth mentioning that some of these features are not very intuitive, and so it takes some time to figure out how it works. If the software lost tracking of one of the markers, it might be possible that it still tracked that marker, but was not sure which marker it is. In that case, it will classify the tracked data as unlabeled. It is possible to then label that marker manually. But to do so, one must first identify which marker it was supposed to be, which in some cases might be very difficult, if not impossible. In cases like this, the errors must be manually adjusted later on in an animation program like Blender or Maya. After the capturing process is completed, you will have to export the animations from Motive. Here, it is very important to choose the correct settings, otherwise importing the animations into Blender could lead to problems. The most important setting is the output file type. This needs to be set to BVH. At first, I tried exporting as FBX, as this is also the file type needed for the Unreal Engine import. However, when exporting as FBX and then importing it into Blender, the skeleton of the file became tilted. While this does not affect the way the animation looks in Blender, it will make retargeting the animation in Unreal Engine more difficult. This issue does not occur when using the BVH file format. The next step is to import the animations into Blender. This step is important because it is needed to add a skeletal mesh to the animations, as the exported file from Motive does not include one. Without one, importing into Unreal Engine is not possible. This mesh could be something very simple like a cube, but I recommend creating a simple mannequin to make previewing the animation in Unreal easier. I created a sample file that can also be used to import and export animations with, which already includes a simple mannequin. It was also necessary to make some small changes to the skeleton that comes with the files exported from Motive. One of those was to change the name of the root of the skeleton to root. This way, Unreal will recognize it as the skeleton's root. I also subdivided one of the spine bones. The Motive skeleton's spine only has 2 bones, while the skeletons in the Unreal project have 3. This led to problems when binding the animations to the control rig later on. It causes a strange squashing issue to occur for the character's spine. It might be that, because there is no bone to draw data from, Unreal sets all transforms of this bone to 0, including its scale. This can be prevented by subdividing the motive skeleton's spine, thus giving every bone a corresponding one. I also added finger bones to the motive skeleton, as it did not have any. It is possible that the same issue I encountered with the spine could also happen with the fingers, so adding finger bones beforehand is recommended. It also gives you the opportunity to already create finger animations from within Blender. In Blender, the animations can be further post-processed. Any remaining tracking errors can be cleaned up here. Theoretically, it should also be possible to clean them up in Unreal using Control Rig, but currently Blender offers more features and a more user-friendly interface. It is also easier to make very exact and fine-tuned alterations than it is in Unreal. This is also where the animations should be cut into a start, loop, and end part if applicable. It also needs to be made sure that the individual sections transition into each other and loop correctly. More specifically, the end of the start section must transition correctly into the start of the loop part. The end of the loop part needs to transition correctly into the start of the loop part and the start of the end part. And the end of the end part must transition correctly back into the start of the start part. In some cases, it is sufficient to simply copy the first or last keyframes from one part to the other, and simply leave a few keyframes empty to create a relatively smooth transition. But most of the time, some bones keyframes have to be tweaked specifically to create a believable transition. This can range from simply removing some keyframes to allow a specific bone to have more time to reach the new pose, to only removing keyframes for a specific channel, to manually creating small transition animations for the particular bone or bone chain. Most of the time, the main difficulty comes from figuring out which bone or rotation axis is causing the problem. All in all, this process took about 1 hour for the animation shown here. For exporting the animations, I found it very useful to use the official Blender to Unreal plugin by Epic Games, as it takes care of all the export settings for you, and also prevents an issue with scaling that might otherwise occur when exporting from Blender to Unreal. It also exports all the animations currently found in the Blender file as individual FBX files. Without this plugin, all the animations would have had to have been exported individually, one by one, which would be very time-consuming. Therefore, it also saves a lot of time and effort. After doing all that, we can now import the animations into Unreal Engine. Now, the animations must be transferred to the skeleton of the character that we are using as the virtual agent. The process allowing us to do so is called retargeting. Retargeting is an additive process that works by adding the rotations of the animation to the base pose of the character the animation is being retargeted to. The base pose is the pose the character has when no animations are applied to its skeleton. The retargeting process itself is fairly simple, as Unreal does all the heavy lifting for you. However, the results might not be very good, as it heavily depends on how similar the skeletons are, as well as on choosing a well-suited retargeting base pose. One of the issues we faced was that the character skeleton had a spine set up using 3 bones, while the motive skeleton only had 2. This caused the animation to appear kind of squashed. Using the retargeting options Unreal provides, we were able to fix this issue for the time being. The second issue was that after retargeting, the shoulder bones of the character appeared to be twisted. Unfortunately, we could not figure out what the actual cause for this issue was, but we managed to fix this particular problem by creating a retargeting base pose. The process of creating this base pose was pure trial and error. The workflow was to adjust one bone of the character in Blender, usually only in one axis, exporting the resulting pose, importing it into Unreal, and retargeting it anew. Then I would compare the results of the retargeting between the newly created pose and the previous pose. This process would continue until I had found a retargeting base pose that yielded satisfactory results. But as you can guess, this takes a lot of time and needs to be done for every skeleton that the animations should be retargeted to. However, even after finding a suitable retargeting base pose, there were still issues with the animations. One of them was that the placement of the hands was off. This is most likely caused by the fact that the actor of the motion capture data was significantly smaller in height than the character the animation was being retargeted to, with the actor being only about 160 centimeters in height and the character approximately 180 centimeters. In addition to that, the proportions in general were different, for example the length of the arms compared to the rest of the body, which probably was also part of the issue. Because of that, more adjustment to the animations was needed. With Unreal Engine 4.26, Epic Games introduced the control rig feature. A control rig is generally used when animating digital characters to make the animation process easier and more intuitive. Instead of transforming the bones of a character's skeleton directly, the controls of the control rig are moved, rotated, or scaled. The transform of the control is then either applied directly to the corresponding bone, or some additional logic is performed to transform the bone in a specific way. This, for example, could be inverse kinematics to not only transform the position of the character's hand, but also to adjust the rest of the arm bones. I created a control rig in Unreal Engine for the Mixamo skeleton we use, and I also started work on a control rig for the skeleton of the scanned avatars, which are also included in the project. The control rig was created by referencing the official one for the Unreal mannequin. Unfortunately, it was not possible to simply copy and paste the control rig, as the bone names, axes, and transformations did not match, as well as the character's idle pose, with the Unreal mannequin being in an A pose and the Mixamo characters being in a T pose. Therefore, the control rig had to be created from scratch. The control rig consists of two parts, the forward solve and the backward solve. The forward solve is used to create and modify animations, while the backward solve is needed to bind an already existing animation to the control rig, so it can be further modified. After binding the retargeted motive animations to our control rig, we noticed that a very similar squashing effect occurred to the one we had seen before. This was the point where I would then introduce the additional spine bone to the motive skeleton to fix this issue. Using control rig, I would then attempt to fix the animations as best as I could. There were many difficulties, especially concerning the rotation of the wrists. When adjusting the rotation of the wrists, they would often rotate a full 360 degrees between one keyframe to the other, instead of using the shortest path. I am not entirely sure why this would happen, but I think it might be because you are basically animating on top of already existing keyframes that come from the bound animation, instead of adjusting the keyframe directly. There would also often be a problem with the way the forearm rotated in relation to the wrist, and the wrist twisting in an unnatural way. These issues might be caused by the character's skeletons not having any twist bones in their arms. Twist bones are a specific type of helper bones. A real-life human arm consists of two bones, which allows the arm to rotate more at the wrist than it rotates at the elbow. The twist bones in a skeleton, for a 3D character, allow to simulate this kind of movement. We also found that for some reason, the animations after being bound to the control rig appeared to look different, so we also had to counteract these differences during the fixing process. To make sure the changes stay consistent between the start, loop, and end part of the animations, these three parts were bound in the same level sequence to the control rig, which was then baked back into individual parts. I would then test these parts once more by arranging them in an animation montage to ensure they still loop correctly. All in all, this process takes at least another hour of work. After adjusting the animations to look good with the standard Mixamo character we use, we noticed that there were problems with some of the other characters. While the characters all use the same base skeleton, making sharing animation between all of them possible, their skeletons are not the same proportionally. Some characters have longer arms than others, or other proportional differences, which resulted in problems with the placement of the hands once more. To solve this, we opted to adjust the animations once more, creating two versions of some of the animations to better adjust for these proportional differences. Another way to use motion captured animations within Unreal Engine is to use its LiveLink feature. LiveLink allows to directly stream motion capture data into Unreal and would therefore eliminate the need for Blender in this pipeline, streamlining the workflow. Unfortunately, the results for the live data were not great, and introduced even more problems with the animations than they would fix. For example, the proportional differences between the actor and the character would cause the hand of the character to appear detached from the rest of the arm, which would be another problem that would need fixing. Therefore, we decided against using this process. In addition to the motion captured animations, I created 3 more animations using the Unreal Engine control rig and the keyframing technique. All in all, control rig works very well, but at least as far as the implementation of it goes in 4.26, I think Blender is still a better option to create animations with. It offers more features and is overall easier to use, in my opinion. I also recorded some sounds and voice bites for the animations to create an additional level of realism and immersion. As I demonstrated, motion capturing is not as easy as one might think. While it can result in some great and naturalistic-looking animations, there is a lot of time and work involved in cleaning up and adjusting the animations for the characters that should use them. It also appears that one should take the proportions and the height of the actor in relation to the proportions and the height of the character into consideration, and try to find an actor that matches the character as close as possible. Despite these issues, the process of motion capturing is still easier and faster to do than to create animations by hand. Especially when working on a project without a trained animator, the motion captured animations will result in better and less robotic looking animations than ones created via the keyframing approach. The second part of this project was to try and find a way to evaluate the quality of the created animations. As there seems to be no standard procedure on how to evaluate animations, I did research on many topics related to creating animations and their quality. One of the results of this process was the animation quality checklist. This checklist consists of mostly things that I noticed during the animation process, but also includes some hints I found in literature. The checklist items are some basic guidelines of what to think about or pay attention to while animating. For example, making sure that there is no clipping or only very little when body parts touch. It also includes some guidelines for the character model and skeleton itself that should be fulfilled to make the animation process as smooth as possible. The most commonly referenced factor I came across during my research in animation quality was believability. However, there does not seem to be a set definition for believability or a standard procedure on how to evaluate it. There are multiple different factors that are being attributed with having an impact on believability. These include gazing behavior, back-channel behavior like nodding, as well as interaction with other agents and with the environment. Another factor which was mentioned in multiple works was personality. In a work by Aaron Loyal, it was even said to be the most important factor for virtual agent believability. Due to this apparent importance of personality, and because it is not yet reflected in the system, I believe that this might be the most promising way to improve the system further. The probably most well-known model of personality are the Big 5 personality traits, also known as the ocean model. Some research exists on how the different dimensions of the Big 5 translate to specifics in a person's movements. For example, people scoring high in the extrovertedness category seem to generally show broader movement patterns, whereas people scoring high in the neuroticism category tend to show more self-touching behavior. These findings could be used to create more or less simple variations of already existing animations to create more variation and in turn to create simple personality variations for the virtual agents, which hopefully could result in boosting the believability of the virtual audience simulation as a whole. Overall, there are many factors and considerations that go into creating high-quality animations. For someone untrained in animation, these are difficult to know and consider. I attempted to make the process a little easier by establishing some very basic points that need to be considered with the animation quality checklist. I have also proposed a possible next step for research focusing on implementation and creation of animations that give the impression that the virtual agents have a personality, which might further improve the believability, immersion, and fidelity of the virtual audience simulation system. Thank you for watching.